present?
I'll present problem 6.
All right, so you're actually to start. Very good. So, welcome everybody. Let us start our session on homework explanation. And we will look at 3 problems, 3 instructors will present the problems. I want to say that we appreciate the number of homework delivered. It's even bigger than previous package. Some of you have made it late. I don't think it matters. In most cases, just 1 hour delay. Some of you apparently have experienced technical difficulties. I don't know why. 2 of you wrote to me. We will sort it out. I guess it will be all right anyhow. Very good. Then let me first enable sharing for course. Right, let me put cars into sport. The floor is yours, please.
Yes. Okay, thanks. Let me see. Is it? All right. So I'm doing problem 6. And in this problem, we're looking at a circular quantum dot, which is written down here. So we're given this potential here. So for this region here, described by these parameters, the potential is 0, and otherwise it's infinite. So if you would draw this region, it would basically be this red line here, or this red area. So you have 2 circles of radius r1, which is r plus r, and r2 is r minus r. And yeah, the region between those circles, that's the part where the potential is 0. But for this problem, we assume that this big R is way bigger than a small r. So in fact, we just have this circle in the xy plane for which the potential is 0, and outside it's infinity. Okay, so let's start with 6a. We're asked to calculate the eigenfunctions of the electron and the eigenenergies. And a hint is given. These psi phi are also eigenfunctions of the operator Lz. Okay, so let's start with that. So you let Lz work on the eigenfunction, and then you should return h bar m times that function. Now you can replace Lz by its operator form, so you have IH bar dg phi, and you can solve this differential equation. And you'll find that it's just some normalization factor times the power of e to the I m phi. Yeah, and this normalization factor is 1 over the square root of 2 pi. You can get it from integrating, yeah, you can get it from this relation here. By plugging this relation into here, and then from that calculating n. So that's the first part. Oh yeah, so on the circle here you have these eigenfunctions, and outside psi phi is 0. So yeah, that's the short version. Yes, and then the energies. So in these, oh yeah, I've introduced polar coordinates. So in these coordinates, the kinetic part of the Hamiltonian is given by this here. So if you let this operator work on the eigenfunctions, then you get Im out 2 times. So it's just, this, from this we get these eigenenergies. H bar squared m squared divided by 2 big M r squared. And this big M is the mass of an electron. Good, so that was A. Now to B. Here we're asked to calculate the matrix elements of the dipole moment. So what does this dipole moment look like? So it's just charge times distance. And charge is E. And the distance here is r cosine phi, and for the x component, and sine phi for the y component. So let us focus on the x component here. So you can write out the cosine, and you get e to the I phi plus e to the minus I phi. And if you let those work on these states m, then this e to the I phi raises it, and the other one lowers the state m. And from this you can this reduces to delta functions here. So that's the expectation value, or the matrix element. And for the y component you get something similar, only you get a minus sign here, and you get a 1/2i. So the matrix elements are given below here. And you indeed see that a state is either raised or lowered. And the second part of the question said, okay, for the process of emission, show that we have this selection rule here. Well, so emission means that you lower your energy, you emit a photon, so your state loses energy. And yes, so for the dipole interaction, this corresponds to the transition of m goes to m minus 1, because the final state energy, em minus 1, is lower than the initial state energy, em. And from that we can deduce this selection rule here. Okay, and then part C, the emission intensity. So we want to calculate the decay rate for emission. And this is just basically Fermi's golden rule, but then you replace the sum over k by an integral. So that's done here already. And I also filled in here the initial and final state energies. So let's look at what those final and initial state energies are. Well, for emission, you have that final state energy is this m minus 1, and you have 1 photon created. And the initial state is just m and no photon. All right, so we need to calculate these expectation values here. Oh yeah, so h int is the dot product of d with E the electric field, and there is some expression in the homework there. I think you all know what it is. And I think there was a typo, because there was this epsilon without the 0. I think it shouldn't be there on the homework. It should be left out. Anyway, we need to calculate these expectation values here. So I think everybody got this. It's just you calculate this expectation value and you find this. You give I times the polarization factor E, where alpha is just 1 or 2, and you have this this coefficient. Good. Then you need to calculate the dot product between D and this polarization factor E, or factors actually. So we need to look at this picture here. It's advantageous, as the question suggested, to choose a polarization for one of the two, which is in the Z direction. So here, that's this one. It's out of plane, so the inner product with this RAB so is always 0. And the inner product between this E1 and R is the only thing we need to worry about. And yeah, well, if you oh yeah, and I introduced here this angle theta between K and the direction R here. And if you fill around a bit, you'll find that it's equal to the sine of theta here. This inner product. It's E times R times sine theta divided by 2, and that's that's what this inner product gives you. Good. Then we can calculate, we can calculate the emission intensity. So we just square this thing, the amplitude, and I'm going from this line to the next. I use this delta function to integrate over the momentum k, and you use that omega k is c times the wave vector k, and then you find this here. So this thing here is the emission intensity, and that's what you were asked to calculate. And only photons with one polarization are emitted because of only one of the polarizations contributed, as I just said as I showed in the previous previous slide. Okay. And then in question D, we're asked to calculate the total decay rate. So that means we just need to integrate this thing here. Well, if you do that, then and you do some substitutions, you get rid of this e squared and put it in this alpha here. Then you find that the total decay rate is given by this. It's a bit straightforward exercise, I think. Good. And then the last question, the bonus question. So initially you are in this state here, in the ground state, and then you're excited by some process to the fourth excited state. And from that fourth excited state, you start to emit photons due to this dipole interaction, and you lower your energy. So you go to third, second, first, and then back to the ground state. And we're asked to calculate photon energies. All these photon energies here, you must calculate. So it's just given by the difference of energies between these two levels. So what that means is you calculate EM minus 1 for M is 1, 2, 3, 4. And you're also asked to calculate the ratio of all these decay widths here. So you just plug in the result. You use the result from the previous exercise. You plug in M is 1, 2, 3, 4, and then you give these ratios. So that's how you solve the bonus question. That was problem 6. I don't know if there are any questions. Maybe I went a bit fast, but let me go back. Where is the?
Yeah, just also wonder why is not okay. So that's a question.
What about the ratio of photon numbers between in 6C? The question is what about the ratio of photon numbers between polarization E1 and E2 in 6C? Well, there are only photons created with one polarization or emitted. So the ratio is just 0. You have because you only create one type of polarization. Photons with one type of polarization are emitted. Does that answer your question, Lucas? Is it okay? But I think it's a trick question. Okay, but the
trick
question is answered. Okay. Right.
Good. Thank you, Cars. So let us. Could you please stop share?
Yes. Stop. Yes.
Right. So I would cancel Spotlight. Miriam, are you ready? Or who is next? Hristo? I don't see Hristo.
I'm not sure who is next, but
Apparently Miriam. Let's see, I got no response from Miriam. There can be technical problem.
Hello, Yuli.
Hi, Miriam. Are you the next? Are you presenting
No, I'm presenting problem 8.
Oh, sorry. Then
No problem.
whatever. Let's try to give the number in. So, Hristo, are you here? I don't have response from Hristo. Miriam, if you are ready, why don't you start and then we can go with Hristo. So let me just put you into Spotlight. Hop. Right.
Yes.
Good. So please.
Okay. So we'll have problem 8 first and then problem 7 after that. I will discuss number 8 and try to share my screen with you. Here we are. So I did not receive any questions from you about problem 8. I did receive a lot of questions about 6 and 7. So I am hoping that that is a sign that problem 8 was not too difficult for you. So let's go through it. It's essentially about calculating decay rates, like problem 6, but in a very different setting. So here it is. You recognize the print from the assignment itself. It's about a qubit, problem 8 here, coupled to some electronic circuit, which we'll come back to later. But first, the problem is described mathematically. As usual, there is the Hamiltonian for the qubit given over here. There's the environment that it's coupled to, consisting of bosonic modes with the usual creation and annihilation operators. And then there is the Hamiltonian of the full system, which includes qubit, environment, and the coupling between the two. And this coupling Hamiltonian is given by the following here, where you see a product of two operators, one acting on the qubit, sigma z, and this phi operator acting on the environment with these bosonic mode operators. So there we are. This is the full Hamiltonian that we're going to work with. And I've highlighted the goal for the exercise in red here, just taken from the problem that you've all had. So our goal is to calculate transition rate using Fermi's golden rule formula, which is given here. And then there were also some useful mathematical formulas, 2 of them that you can use along the way. So part A. Part A was asking us to determine the initial state and all the possible final states for this problem. And then to diagonalize the qubit Hamiltonian, HQ, and find the corresponding eigenenergies. Now, how do you do this? I think more or less all of us will have done it in the same way. Initial state and possible final states. You just have to read the problem carefully and then think what it means, what the words mean, and translate them into kets, so to speak. So if something can decay, it must be in a higher state than the ground state for sure. So in the initial state, if you read the problem well, it should consist of the qubit being in the excited state. The qubit only has 2 possibilities. It can be in the ground state or in the excited state. And it starts out in its excited state. And it was also given that there are no bosons. So if I write this in terms of kets, then my initial state here will be a combination of the excited state for the qubit, which I denote as E, and the vacuum state for the environment, which I denote as 0. And if you like, then you can also shorthand this more into something like this, E0, the 2 parts for each of the 2 elements that we have, qubit and bosonic modes. Fine, that's our initial state. And then it can decay. And which are the states that it can decay into? Well, the qubit obviously will decay to its ground state, which we'll write as G. And then there will be 1 bosonic mode being created. Let's label it M. So the possible final state, which is a whole collection, consists of the qubit being in its ground state always, and 1 bosonic mode with index M being created. And just like I did here, I can also shorten this into this notation, G, and then something like 1 boson with label M, 1M. So that's the initial and the final state. And then now we are looking at the qubit specifically and diagonalizing its Hamiltonian. So the energies, well, okay, let me just scroll back. It's not so difficult because the qubit Hamiltonian is simply a 2x2 matrix. If you substitute these 2 into the expression here, you can directly diagonalize this 2x2 matrix, and that will give you the eigenenergies. So I skipped all the steps, assuming that the 2x2 matrix diagonalization is fairly straightforward. And if all is well, you'll have found these eigenenergies, square root of E squared plus T squared, where T is the coupling energy of this qubit, and it can have either a plus or a minus sign. So then the ground state has the lower energy consisting of the minus sign, minus square root E squared plus T squared, and the excited state will have the plus sign, plus square root of E squared plus T squared. And this is only the qubit part. And we were asked to determine the total energy of both the initial and the final state. So the initial state is easy. We said that the qubit is in its excited state. There are no bosons, so the total energy will be square root of E squared plus T squared. But in the final states, the qubit will have decayed to its ground state. That corresponds to this energy Eg that we found. And there will be 1 bosonic mode, which has the usual energy h bar omega n. So the total energy for the final state is this thing here, minus the square root plus h bar omega n. And that concludes part A. We've diagonalized the qubit Hamiltonian and determined the initial and final states and their energies. Now it goes on. Now we're going to look at the transition matrix elements. So we're going to look at the interaction Hamiltonian that couples the qubit to the modes, to the environment. And we are going to express this matrix element in terms of Fm. And Fm, you remember, was this coefficient, was part of this operator phi, which is the amplitude of this operator acting on the environment. So how do we calculate this matrix element? Well, you substitute the expression for the Hamiltonian directly, and then you manipulate the operators a little bit. So here it is. This is the matrix element, which couples the initial to the final states. I simply substitute the given expression for the coupling Hamiltonian, which is this thing here. Nothing mysterious. All constants go in front. And then I substitute the expressions for sigma z and for phi. So sigma z just stays like it is for now. And the operator phi we can express as a sum over creation and annihilation operators as given. There is the initial state over here, qubit in the excited state, 0 bosonic modes. And there's the final state over here, ground state, and 1 boson being created. And now, in my case, what I did is I let this sigma z operator acting to the left. You remember, you have a choice here. You can also switch the order of the operators if you like, but I simply let this sigma z act on this state here, and then the bosonic modes here are left. And if all is well, you find out that only when this index n is equal to the m that I'm looking at, this operator will actually yield a non-zero result. And if you put all of that together, then you just find this expression. Hopefully all the signs are correct. I think they are, a minus here and also a minus here. And then there is this Fm, which is the only coefficient left that yields something finite. And writing it a little bit more nicely, I end up with this expression for this coupling matrix element. And you see it contains both qubit parameters, if you like, the E and the T, and it also contains Fm, which corresponds to an environmental amplitude. So this is the essential ingredient for Fermi golden rule. So I see a question from Frank. What eigenfunctions do you use? Where do you mean, Frank? Is that in this matrix element here? There I use the eigenfunctions. I haven't shown them. That's good that you ask. For the qubit E and G, which are two-dimensional vectors corresponding to these eigenenergies. I haven't shown them on my slide here. That's true. But you remember we diagonalize this 2x2 matrix, find eigenenergies, and to each of these eigenenergies, there's a corresponding eigenfunction, and that is the one that I use to obtain this result here. So this is also a 2x2 matrix, sigma z, and then it acts on a two-dimensional vector. And in this case, for the bosonic mode part, you directly apply the caps to the eigenfunction, as usual, as in many other homework problems. So yes, it is easy to make little mistakes. We'll check your problem very carefully, as always, and just look at the steps that you've taken. And if there's just a little mistake, it won't cost you many points. So this is the matrix element. And now it goes into the rate gamma, Fermi golden rule expression given in the problem. So you can simply substitute your result in there, and then you have to sum over all the final states, m. So here it is, the expression for the matrix element squared. And there is the delta function, which selects the correct energy. And it's just the difference between the energies of the two states, EE, and the energy of the excited state, and the energy of the ground state, plus the bosonic mode here. So if I rewrite this a little bit into a nicer form, I put all the constants that don't depend on m, I put them in front again, and then there is the sum left of fm squared, and the delta function is also a little bit rewritten by substituting the explicit expressions for EE and EG. So this is your rate, expressed as a sum over these fm squared. Now we're going to look a little bit beyond this first mathematics, let's say, and now we're actually going to look at the physical parameters that we have, which are the E and T that we've met already, but there was also the electronic circuit with a resistor and an inductor and this I0. So we would like to express our rate that we found here in B, our end result from B, in terms of the elements of the circuit. And that goes in a few steps. So in part C, first we have to derive the equations of motion for the caps, for the operators BM and BM dagger. These operators are governed by this Hamiltonian, which is also given here. So there is h bar omega m b dagger b minus another operator that also depends on this creation annihilation operators, b for the bosons via this phi. So we're going to derive the equations of motion, and then we're going to use a Fourier transform to express them as a function of frequency, omega. And the approach is quite straightforward. There was a formula given to derive equations of motion, so we're going to use that formula, and then we're going to use the Fourier transform, standard Fourier transform, to the expressions that we found to calculate this response function, chi of omega. So this general equation was given at the end of the problem that you received. And if I apply it to the operator Bm, and I use as Hamiltonian the given Hamiltonian over here, this one, then substituting everything in here and using commutation relations, again, you have to do some manipulation of the operators here in this equation, and use the commutation relation for Bm and Bn dagger, then you should come out with the right result, hopefully. So if I do all of this, I find that the time derivative of the operator Bm dot, is equal to minus I omega m times Bm, plus this additional term, which comes from the second part of the Hamiltonian here, and reads I over h bar, current, time-dependent current, times Fm. And there is an analogous equation for Bm dagger. You just have to take the Hermitian conjugate on the left and on the right of this equation. So this is the equation of motion for the operator Bm. Equation 1, it's numbered here. And once we have that, we can apply the Fourier transform to the operators Bm and Bm dagger, and also to I, the current IT, and substitute those and use that to transform this entire equation of motion. So Bm is now replaced by its Fourier transform, which is the following expression here. It's a time integral, Bm time dependent, and then there is this complex exponent in which this S here is the frequency plus an exponentially small imaginary part, I times epsilon, epsilon very small. I also need to arrive at the response function chi. I also need to Fourier transform this operator phi. The definition is here above here. And if you do that, you will find that this operator phi omega, the Fourier transformed operator, looks like this here, where again you have this omega and plus I epsilon in the denominator. And this expression, if you do the full calculation, will have two parts, one applying for positive omega, and then there's another term for negative omega. But since we were asked to look for the term that has positive frequencies, I only show that one here. But probably you found another one that you then discard. Now we're almost there, because once we found phi of omega, then the response function, just as also discussed in the lectures and in the book, is nothing but this coefficient here that links the Fourier transform current to the phi here. Phi omega is chi omega times I omega. And so we now have all the ingredients. We've found phi omega. We found I omega by Fourier transforming the current, IT. And then if you look at chi, or more precisely at its imaginary part, which we were asked for, then it will have the following expression. It's a sum of over the bosonic modes. Then there is the delta function, selecting each bosonic frequency, omega minus omega m, and the amplitude that goes in front is again proportional to Fm squared, just like for gamma, for the decay rate that we found before. So this is the response function that we were looking for, imaginary part of chi omega. And that now becomes nice to consider in terms of the actual physical parameters that we have, because now in the next part, we have to express this response function by actually looking at the physical circuit that the qubit is coupled to. And there's also a hint. The hint is that it's given that the voltage drop over the coil here and over the resistor on the other side is the same. Now, that's something that we can use. So we're now considering the following circuit, which is an RL circuit in parallel, if you like. And we also know that there is an equal voltage drop across the inductor and the resistor. And given that, you can analyze this circuit and translate this into formulas. So one way to do this is, what I did is I assumed that the current that arrives here splits, of course, across the coil and across the resistor. And I just assumed that there is a certain part of the current, let's call it alpha, that will flow through the resistor. And then there must be the rest of the current, 1 minus alpha, that is flowing through the coil. And alpha is a number between 0 and 1. If you do that, I can express this knowledge that I have, namely that the voltage drops equally across L and R, in terms of just by writing what this voltage actually is. There's the resistor part, there's the inductor part, they should be equal. And you also know that the voltage is given by this expression here, alpha, so the current alpha I times R. And if I then Fourier transform, because these are two time-dependent equations, and I'm again interested in the frequency domain. So I Fourier transform these two equations, and that leaves me with the following somewhat lengthier expressions, but not too difficult. Direct Fourier transform of 1 and 2. And then I eliminate this alpha, which I introduced, and also let this tiny imaginary part go to 0. And then I actually find frequency-dependent expressions. And if I do this, I end up with this response function taken from the previous part. I substitute my results from here in there, and then I find that chi is RL over R minus I omega L. Taking again the imaginary part that we were interested in, we end up with an expression like this. So now we've expressed the response function in terms of the elements of the circuit, the resistance and the inductance and the frequency, which is nice because it actually makes a connection between more mathematical expression to an actual physical circuit. And now most of your work is done. There's just a bonus question left, which in this problem was not very difficult. I think it was essentially a matter of substitution. So the bonus question was asking you to compare your results of C and D. C, this expression for the response function, and D, the expression for this response function in terms of R and L and so on. So comparing those means basically substituting one into the other. And if you do that, you end up with a longer expression, but it's a very straightforward substitution. So you'll have something like this. Now gamma, which is the decay rate of the qubit coupled to this bosonic environment, can be expressed in terms of R and L and the qubit parameters E and T and some constants as this thing here. Usually in your homework, I see different varieties, but most of the time they boil down to the same expression here. So we will check it for you. That concludes, I think, homework number 8. And I'll be handing back to Yuli. Thank you very much.
Thank you, Miriam. Thank you, sir. There are no further questions. Then we switch to Hristo. Let's see. Hristo, are you here?
Okay. I put everything on.
Good. So please, the floor is yours.
Okay, I'm sorry for being late. Now, in this presentation, we're going to talk once again about the Anderson model. And this time, we're going to go a little bit further and also express the decay rates from the delocalized level to the metal. So one more time, as an introduction, the problem consists of a localized level and a conductor, a metal, and this localized level can have only 0 electrons, 1 electron, or it can be doubly occupied. The electrons in the impurity, again, just so to make sure the fixed notations are described by the operators denoted by D. And the impurity Hamiltonian, so the impurity Hamiltonian has interaction energy, meaning that if there are 2 electrons on the side, they interact with each other with this strength U. And further, the electrons in the metal are described by the usual way, meaning that all the electron states are filled up until the Fermi level. Yes, and this is our ground state of electrons. Now in question A, you're asked to do the same exercise as in homework problem number 5. So neglecting the interaction between the metal and the impurity level, you're asked to give how many states, how many states are possible at the impurity. So for, I guess this is quite simple, but I'm going to repeat it. So you can have 0 electrons, then the spin, you don't have any spin. The energy is 0 according to the Hamiltonian, and we denote it with just a ket 0. Then we move to 1 electron. You can have up or down. It has an energy epsilon plus U, and you have 2 states. It's either, yes, you either generate or create electron with spin up, or you create electron with a spin down at the impurity. Then we move to 2 electrons. You can have 2 electrons at the impurity. It's either up down or down up. Those are 2 equivalent states. And they have the energy, both of them have the energy 2 epsilon plus 4u. And again, this is how you can express the two states with creation and annihilation operators. Then we move to question B, which is different than homework problem number 5. Here, you're asked to consider the energies that are required to remove an electron from purity, putting it to the metal, or inversely to take an electron from the metal and put it into the impurity. And to give some conditions on the energies epsilon, the Fermi level, and the interaction energy, under which the ground state of the system corresponds to no electrons at the impurity. So we first look at the energy difference between, so this E1 minus E0 describes the energies at the impurity level. So we look at singly occupied impurity minus the energy of the zero. It's quite natural, we've seen it before. The energy is just epsilon plus u. And then the next situation can be if we have 2 electrons at the impurity, and we take the energy difference between 2 electrons and 1 electron at the impurity. Bear in mind, we have already evaluated those energies, so it's just this 2 minus this 1. So we obtain epsilon plus 3u. Now, in order not to have an electron at the impurity, we must verify two conditions. First, the first thing is that the Fermi level must be below the energy difference between 1 and 0 electrons at the impurity, meaning that if there was a single electron at the impurity, because of the fact that the Fermi level is lower, then the electron will move close to the Fermi level and will lower the energy of the whole system. That's why we have this first condition. And then we also need to make sure that for 2 electrons, also 2 electrons at the impurity, the energy of 2 electrons at the impurity is higher than having 2 electrons at the Fermi level, in order to make sure that there are no electrons at the impurity. So those two conditions combined will give you the following condition for the Fermi level. And again here, this condition will also mean that the interaction energy is positive, that the electrons on the impurity level repulsive interaction. Okay, I have a chat. Yes, there might be a question. If it takes a lot of time to write up, you can speak up. How you combine them? Well, you just have 2 inequalities, and it's the same Fermi level. So if I divide, for example, the right equation, let me use green here, I divide it by 2. Can you please speak up? It will be easier than writing.
Yes, I don't get it, because in both cases, the Fermi energy is smaller than another quantity, right? So on the left inequality, the Fermi energy is smaller than epsilon plus u, and on the right inequality, again, Fermi energy is smaller than epsilon plus 2u, but then in the combination of them, the Fermi energy is between 2 different values. This I don't get it. Or maybe I'm getting something wrong. I don't know. It just confuses me.
Fine. Or did I have a mistake? Sorry, yes, here I have a mistake apparently, because you see this inequality, EF is bigger. Yeah.
I think one of them is sufficient. Yeah. The other one is automatically, how do I say, realized, yeah, the one with 2 electrons is automatically higher than the one with 1 electron.
It depends if it's positive, right? If it's negative,
Yeah, sure.
You can lower the energy.
Okay.
Yeah.
Okay. Maybe I think about it more, but here I don't get it. Thank you.
Okay. Okay, then we move to question C. So what we have in question C, we will be, I'll read it for you, just so we fix the problem. We'll be interested in transitions from the doubly occupied impurity state, and we'll consider 2 situations. The first situation is to go from the doubly charged impurity that loses 1 electron to the metal, becomes singly charged, and then loses another one. And then the situation B will be for the doubly charged impurity that cannot lose a single electron, but can lose immediately 2 electrons. So it loses simultaneously 2 electrons. And you're asked to give the conditions of the energies under those situations. So in situation A, it's quite straightforward. If we have evaluated the energies, we go from 2 electrons to 1 electron. And for this, the energy difference between 2 and 1 must be greater than the Fermi level, energy. And then again, going from 1 to 0, it's the same condition. The energy difference between 1 and 0 state must again be greater than the Fermi level. So this is the situation A. Then situation B. So what we have here is going from 2 electrons immediately to 0 electrons at the impurity. In order to go from 2 electrons at the impurity to 2 electrons that are close to the Fermi level, what we need to assume is that the energy of 2 electrons at the impurity level is bigger than 2 times the energy of the Fermi level. And this will give us the first condition on the interaction energy from this. But we also need to make sure that it is not possible to have a single electron at the impurity. So that means that the energy of having the energy difference between having 2 electrons and 1 electron at the impurity is smaller this time than the Fermi level, such that it's not possible to have this transition. And from this transition, we obtain our second, here in yellow, we obtain our second condition for the interaction energy. We can combine those two, and we end up with a single double inequality for the interaction energy. And you can see that this is only possible if actually the energy EF minus epsilon is negative, meaning that U is also negative. So this type of transitions of having 2 electrons going to 0 would only be possible if the interaction energy is negative, meaning it's attractive. The 2 electrons lower their energy if they're combined at the impurity. Okay, then we move to, okay, here I have again introduced just the coupling Hamiltonian in order to have it, because we didn't need it previously. The only assumption and the difference between problem 5 and problem 7 is that here we will assume that the electron energies are close to the Fermi level, and you're given some assumptions about the energy scales. So the energy difference between epsilon, so the impurity level, the energy difference between the impurity level and the Fermi level is very small in absolute value compared to the Fermi level, and also the interaction energy is small compared to the Fermi level. And of course, the usual assumption is that the density of states is energy independent. It's a constant taken at the Fermi level. Okay, now we go to the question D. We are first going to concentrate on situation A and give the initial and the final states for the first and the second decay process. And we're gonna evaluate the corresponding transition matrix elements. And from the transition matrix elements, we're going to compute the transition rates for this situation. So the states are the following. Here I'll denote them with blue. When I talk about them, we have the ground state. The ground state denotes the metal field up until the Fermi level, then one electron would spin up at the impurity. I write it in the following way. One electron would spin down, again with creation operator at the impurity level, and two electrons at the impurity. Now the possible transitions are the following. We can go from two electrons, so up, down, going to one electron having a momentum q with spin down, with the momentum q with spin down at the metal, and we're left with one spin up at the impurity. Or we can do the opposite, so we can transition from two electrons at the impurity to one electron with spin down at the impurity and one electron at the metal with spin up and momentum q here. Okay, now the next we need to evaluate. So we have given the initial and the final states for the first and second decay process, and then we need to evaluate the corresponding matrix elements, and from there compute the transition rates. So I don't write here. I write the matrix element from 2 to 1. I have taken one of them. I have taken the following. So you see here how I write the initial and the final state. Now this is a transition from 2 electrons at the impurity to 1 electron at the impurity. And what we have is, because it's on the left, we have a creation. Okay, here is an annihilation operator, but it acts on the left side. So we have created also an electron with spin down at the impurity level, at the metal, with the momentum q. And this momentum q must be bigger than kf, because all the states are filled up until the Fermi level. Now here I only give you the answer for the matrix element. I don't show how to evaluate this. Hopefully I did not make any mistakes, and it was clear how which term in the mixing Hamiltonian will give you this non-zero contribution. So I have denoted it with a specific color here on the left, and I'm gonna go and show you which term contributes to the matrix element. So it's this term in pink. This will be the non-zero term that will contribute to the matrix element in this transition. Okay. Then we evaluate energy difference, and the energy difference, again, we have 2 electrons at the impurity minus 1 electron at the impurity and 1 electron at the metal, with this time with a momentum q, and we find the following energy difference. Sorry, here on the right. Then our next task is to compute the transition rate from 2 to 1. So we write the usual formula. It's 2 pi over h bar. We have to sum over all q's that are bigger than kf. We have the delta, which implies energy conservation. So this is our energy conservation between the final, the energy difference between the final and the initial state. We have the square here of the matrix element. We have evaluated here, and there is a factor 2 because there are 2 levels that we can transition from and to. Then our next task is simply to use the assumption that is given in the text, to assume that first transform the sum into an integral, because we sum over all momenta that are bigger than kf. The integral goes from the Fermi level to infinity. With the usual change from sum to integral, we have the density of states that we have assumed also to be constant around the Fermi level. And we have the delta function here. It's a pretty straightforward integral to perform. It gives you 1. And finally, we obtain our rate here from 2 to 1. Okay, then we're gonna move to the next. As they're asked, we need to evaluate also the transition rate from 1 to 0. Here again, it's the same slide, but things have changed a little bit. The same slide, the same structure of the slide. We have the matrix element, the state 1 at the impurity level, and we have state, so the ground state of the metal, and we have generated and we have generated 1 electron with spin up at the impurity, at the metal, that has a momentum q which is bigger than kf again, because all the states are filled. I don't show again the full calculation of the matrix element, but we can look again at the color map. So here I have used green, and see which one of the terms in the Hamiltonian, in the mixing Hamiltonian, has a non-zero contribution to this matrix element. And this is the term that has non-zero contribution in green. Okay. Our next step is to evaluate the energy difference as previously. The energy difference is just 1 electron at the impurity, epsilon plus u, minus 1 electron that has a momentum q at the metal. And we have the same sum. We have to sum over, to evaluate the transition rate, we need to sum over all momenta that are bigger than kf, and we have the same structure as previously, only the energy differences are different than before. We also perform the same integral here. I don't write it, but in the same manner, and the same assumption for the density of states close to the Fermi level. And this time we find that the transition rate from 1 to 0 is half of the transition rate from 2 to 1, because there are twice as many final states for a transition from the W state to 1 state. Okay, and then we move to, so question E is a little bit more involved. I think I'm going to read it quickly for you. So in the theorem of quantum transitions, an interesting situation takes place where the perturbation, here the perturbation is going to be our mixing Hamiltonian, causing the transition does not have matrix elements between initial and final state, yet has matrix elements between initial, final state, and a set of intermediate states that are called virtual states. In this case, the effective matrix element between, so this is an effective matrix element between the initial and the final state is given by, and you're given a formula and also some hints. So initially we need to find the initial, final, and virtual states for this situation. And you're given the hint that the virtual states are actually the final states of the first decay process considered in point D. And you're asked also to compute the matrix element between initial and final states in this situation. Now here I only write them. So the initial state would be the impurity level with 2 electrons. The virtual states will have 2 virtual states. And they are the following: 1 electron at the metal having a momentum q with spin up, and 1 electron at the impurity with spin down. And the inverse situation, we have 1 electron with spin down with momentum q at the metal, and 1 spin up at the impurity. And finally, well, the final states are given by the following expression here. We have just generated 2 electrons at the metal with momenta Q, sorry, K and K prime. I write here K and K prime with different indices just to not have any confusion. So K and K prime and 2 different spins, spin up and spin down. So they might occupy different levels in the metal. It might be at K or K prime. And yeah, 2 different spins because initially we had 2 different spins in the impurity. And now from the previous expression, we observed that we need to calculate the energy difference between the initial and the virtual states. So this, in both cases, the initial state is doubly occupied impurity, and the virtual states are singly occupied impurities. So this is what we find for the energy difference. We have done it previously for those states. And the next step is to evaluate the matrix element. Now here I do not present, I'm not going to present every detail of the calculation. First, I'm going to try to just write down the matrix element, describe each term, and then look at which of the mixing, which of the terms in the mixing Hamiltonian give non-zero contributions. So using the previous formula, first we have the sum over all virtual states, and we have 2 virtual states. That's why we have this. This is the, sorry, let me use another color. We have this as the first, and this as the second. We have the sum of those two virtual states, 2 sums. Then for all virtual states, we need to sum over all possible momenta Q. Those are the virtual states. So 2 virtual states with all possible momenta Q. Then here, what we write, for example, in the first expression, what do we have? We have, here we see the final state, 2 electrons at the metal and the ground state that is mixed with 1 electron at the metal and 1 electron at the impurity. And again, the same thing here. We have 1 electron at the impurity, 1 electron at the metal, and here we have the state which has 2 electrons at the impurity. Right? If we look at the formula, final and initial. So the final state is 2 electrons at the metal. Initial state is 2 electrons at the impurity, and here we find 2 electrons at the impurity. And so we need to evaluate these type of combination of creation and annihilation operators. Yeah, I've also forgot we have in denominator, we have the energy difference that we found previously. Now I have only denoted again with color here. You can see for 1 and 2, which will be the terms that will be non-zero in the mixing Hamiltonian, that will give non-zero contribution to this matrix element. And if we go back, I'm just going to show it to you. We go back. I have denoted them here. So this will be the non-zero contribution for the 1, and this will be the non-zero contribution for the 2. Those terms below the numbers will give non-zero contribution. I hope you saw it. We can move on. Okay, we come back to our sum. Then again, we need to perform, well, the same for the second virtual state, but it only differs by spin. So we expect that it will be very similar to the previous term that we looked at. Again, I don't think here it's necessary to describe, but here we have 2 electrons. So this is the final state. Okay, let me use yellow. This is the final state, the initial state, and all in between here. Here are all the virtual states that we sum over momenta Q. And finally, by combining all this and evaluating the matrix elements will give the same term as previously. They will give gamma they will give the prefactor in the mixing Hamiltonian squared. They will give you this coefficient, but this time squared, because we have two of those matrix elements. And then we have the sum over two terms. Now here, of course, we have two different momenta, k and k prime. Those two different momenta, k and k prime, must be bigger than kf. Again, same reasoning, because all the electrons fill the metal states up until the Fermi level. Same denominator in both cases, just a different index for the two energies. Now, I think with this, we finish the usual, so all the questions. And the next question is, again, a bonus question. I'm not going to discuss it in detail. Again, I'm just going to give a general direction of how you should, maybe if somebody has tried to do this question, I'm going to give you a general interlude of how to calculate the total, so how to compute the total rate. So the total rate here will be the sum. So first, I have a small mistake here. There must be a k prime in one of the, so here it's gamma 2 going to k up, k prime down. There is a prime here, but the total rate will be the sum over, so first we need to sum over all possible k's, not k primes, but only k, of this matrix element times, again, energy conservation of the energy difference between the final and the initial state. This is the usual formula. We have evaluated previously, let me use red, we have evaluated previously this, this matrix element between the initial and the final states with all transition rates. Yeah, I forgot here to write the sum over k. Here there is a sum over k, sorry. And we need to take the square of this matrix element, write down the energy difference being what? The initial state having 2 electrons at the impurity, minus having 2 electrons with different k and k prime at the metal. So here is the energy difference. And we have the matrix element that is squared here. It's the usual procedure. From the sum, we go to the integral, introducing the density of states at the Fermi level, which is assumed constant. And then we end up with a certain prefactor, and the matrix element squared, but that is multiplied with the energy difference between the initial and the final state. This will greatly simplify the integral, because the only thing that's needed is to replace actually E with 2 epsilon plus 4u minus epsilon of k prime, right? Here we have performed this sum into integral by transforming k into E. So we're left, again, this will be the intermediate total rate, which still depends on k prime. This is our final answer after integrating. And in order to compute the total rate, we need to sum over all k primes. And yes, so here I write it. We have performed already this sum over this transition rate. Now we need to sum over all k prime. Here there is, so the first thing that we need to do, again, transform the sum over k prime into an integral. I still write it as d e prime. And we have the matrix element squared, so the previous result that we saw. Here there is also a momentum conservation that needs to be assumed. So all the energies that are above this energy, 2 epsilon plus 4u minus EF, will be 0. And we integrate from the Fermi level until this energy. And we have the previous result this squared. Now I don't show the final result, but one way to perform this integral is to expand this this term, obtaining just the usual, the first term squared plus the second term squared plus 2 times the multiplication of those two. Now, this is where I would end, but this is quite easy to integrate. You would obtain 1 over this term with some energy difference. This is also 1 over integral. And for this final term, one can perform partial fractions, for example, and also obtain a result. But with this, I would like to stop. So this was my presentation. Do you have any questions about it? Or I give the floor to Yuli.
Yeah, I don't see there are questions. Kind of, I don't know what does it indicate. Good. Thank you, Hristo. I will talk a little bit about organizational matters and let us see what we shall discuss is examination. Let me tell you something about the examination. We will pass soon an official announcement with all the details. We delayed a bit because we still have to iron quite some details. So the exam commission has stamped our proposal for examination in new conditions, but still we need to elaborate on technical details. There are many. Let me, before official announcement, just let me make 3 important statements about examination. It is no statement that it will occur online. And I would like to stress 3 things. First of all, most important one. Despite the fact that it's online examination, we will make it as similar as we can to examinations which have already happened. So it is still true that in order to prepare to this exam, you have to look at old exams. All right? There are many samples of old exams available. If you look at it, you would understand that it will have all a similar structure, and we will keep the same structure for online examination. With important difference, your exam tasks, your exam assignments won't be identical as it used to be the case for usual examinations. All these assignments will be individualized. I don't know whether it's news to you. I don't know whether you have already passed some exams with individualized assignments. So I don't disclose all details how we will individualize it, but right. the individualization will happen, and simultaneously we have to keep the same level of difficulty. The level of difficulty must be identical for everybody. So please be aware of that. Okay, another important point is that we will have kind of training exam. We are not sure yet about the date. I guess realistic dates are somehow near June 10th. Right. It is for you. You have an opportunity to try. It's also for us because we have to check all numerous technical details which have not yet been proven experimentally. So there will be a training exam. Needless to check, we don't have a resource to check the results of this training exam. But, well, we will try to make it as similar to a real exam as possible. Right. That's the three important things I wanted to tell you before official announcement about the examination. Are there any questions related to this topic? That's pretty strange if you would have plenty of questions. But, all right, let us postpone all these questions. Yeah, could you repeat the possible date for exam? For exam, the date stays at its scheduled. The date, if I remember correctly, is June 29th. We will have a training exam that we would schedule on something like June 10th. Does it answer your question? All right. Good. So please be prepared for that. And right, technical details can be a little bit confusing, but please don't get too much stressed about technical details. The most important component is correct answers to exam questions, and I'm sure it will be all right. Good. So if there are no other questions, let me conclude this session. Let me thank you for your attendance, for your attention. So I will see you on Thursday, I believe, for the last lecture of this course. So I'm ending this session by